Hello everyone, welcome to the GGM YouTube channel. Last week we did some similar triangle introduction, we just did some basic geometry. And this week we'll be doing right and similar triangles, which many of you have probably already heard of. But we will be doing some more difficult problems with these that you might not be used to. So hopefully this exposes you to more difficult types of problems using these concepts. So without further ado, let's continue. So we're just going to do a very quick review of similar triangles. So in the last video, we also mentioned similar triangles. So similarity is when two triangles are the exact same, except one of them is larger or smaller than the other. Thus, the angles are all going to be congruent. But the corresponding side lengths all share the same ratio. So they're not necessarily the exact same, they just share the same ratio. So if ABC is similar to DEF, that means AB over DE equals AC over DF equals BC over EF. We have SSS and SAS similarity as before, so if all the sides are in the same ratio, the triangles are similar. Or if we have two sides in the same ratio, and the angle between them is congruent, the triangles are also similar. We also have AAA similarity, or we sometimes just call this AA similarity since we really only need two angles. Since we only need the angles to be congruent, if all three angles are congruent, then the two triangles are similar. And last week we also went over why there is no ASA similarity on this page, and that is because we only need two angles, so we don't need the S. The S is completely unnecessary. If we have two angles, we know that the third angle also has to be the same because 180 is the sum of all three angles in the triangle. So here's just a similar triangle problem to get you familiar with the concept. Triangle ABC is a triangle with AC equals 3, AB equals 5, and BC equals 6. If ABC and DEF are similar and DE equals 20, what is the perimeter of triangle DEF? So I'm guessing this problem was very easy for you. We know that DE is equal to 20 and that AB is equal to 5. So we can clearly see that the ratio that they all share is going to be 4, right? Because DE is just 4 times AB. So overall, we're going to have EF is 4 times BC and DF is 4 times AC, right? So DF is going to be 12, D is 20 as we already mentioned, BC is, EF is 24. So our final perimeter is 56. Or you could also do this by just adding everything in ABC and then multiplying by 4. As mentioned before, right triangles are triangles that have one right angle, and this is just an angle that measures exactly 90 degrees, or 1/4 of a circle. So we didn't really go over this last time, but these triangles have some very special properties. First of all, we call the two shorter sides legs, and the longest side the hypotenuse. So if you didn't already know these names, you should probably jot them down because they're very important. So for example, if C is 90 degrees, AC and BC are legs, and AB is the hypotenuse. The hypotenuse is always on the opposite side of the right angle. The altitude is the same as the height for the two shorter sides of the triangle. So this makes areas very easy to calculate. So find the area of the triangle ABC if AC is equal to 6 and BC equals 9. So this should have been a fairly easy problem. We know that the area of a triangle is equal to 1/2 base times height. And in any respect, if we choose BC as our base and AC as our height, because again, they form 90 degrees, right? Then we just have 9 times 6 divided by 2. Always remember to do that, and we have 27. And we could also choose AC as our base and BC as our height, and we'll get the same result. We have also seen that we can find the area of a right Okay, we have seen that we can find the area of a right triangle by multiplying the two legs together, and we can also find a relation between the length of the hypotenuse and the lengths of the legs. So if angle C is 90 degrees, AC and BC are legs, and AB is the hypotenuse, the Pythagorean theorem states that AC squared plus BC squared is equal to AB squared. So the sum of the squares of the legs is equal to the square of the hypotenuse. So before we get into the problem, I just want to give you a nice visual. So let's have a nice proof of this right here. So let's say that we have our right triangle ABC as shown. And this is going to be a right angle right here. Okay, so what we're claiming is that the square formed over here plus this square formed over here, is going to be equal to the area of this square over here. Sorry, these are not the best squares, but so there's actually a really nice proof of this. So if we just take our triangle, right, which I'm just going to draw again, and it's just totally visual proof, right? If we have our triangle here and we draw a square, so again, this is not really the best square, but now we can sort of extend these over here. And so something nice about this, let's call this side B and this side A. So now we have 4 duplicates of our triangle. So we can call this A, this is A, this is A, this is B, this is B, this is also B. And this side we'll call C, so this is all C. Okay. So now we can see we have our big square, right? And the area of that is A plus B squared. And something nice you can notice is that if we take this big square, which, by the way, this is equal to A squared plus 2AB plus B squared, and we subtract these triangles, which the area is going to be 1/2 times AB, right? So, like so. And there's 4 of them, so we multiply by 4, so that's going to equal 2AB. If we subtract the area of these triangles, we're going to have A squared plus 2AB plus B squared minus 2AB. And of course, that's just going to equal A squared plus B squared, right? But look at what that also equals. If we take this big square and remove all the triangles, what do we have left? We just have the square with the side of C, so we only have C squared. So A squared plus B squared is equal to C squared. So let's try a problem like this. If AC is equal to 3 and BC is equal to 4, what is AB? That is our first question. And second of all, let's say AC equals 5 now, and AB is equal to 13. What is BC? Sorry, that should be BC. I don't know why that's AC. So I'll give you 5 seconds to pause the video. Alright, so this problem is fairly straightforward. We have AC equals 3 and BC equals 4. So AC squared is 9 and BC squared is 16. And we add them together to get whatever AB squared is. And 9 plus 16 is equal to 25. So 25 is equal to AB squared, and if we take the square root of that, that's going to be 5. So 5 squared is equal to 25, so AB equals 5. And if AC equals 5 and AB equals 13, well, we know that 13 squared is 169, and perhaps that's not common knowledge, but you can verify that quickly by yourself, or very easily. And AC squared, that's 25. So 169 minus 25 equals 144. And 144 just so happens to be 12 squared, so BC is going to be 12. So here's some problems involving right triangles. If we have a right triangle ABC with right angle at C, and we have AC equals 3 and BC equals 4, what is the length of the height from C to side AB? I'll give you 5 seconds. Okay, so we have our triangle ABC right here, and we want to find, and it's a right triangle, we want to find the length of this altitude to AB from C, CD. Okay, so let's say the altitude from C to AB hits it at some point D, right? And it's going to form a right angle. We want to find the length of that. So a good way to do that is realize the triangle has area 1/2 times base times height. And now we can just set BC to be the base, for example, AC to be the height. So we have 1/2 times 3 times 4 equals 6, and that's the area of ABC. And now a nice thing you can do is you can set AB as the base, and CD is now going to be the height. So now we know that 1/2 times AB times CD is equal to 6, right? Because you're always going to get the same area no matter what base and height you use. So we know AB is equal to 5, so we have 5 times CD equals 12. So CD equals 12 over 5, or you can also use mixed number notation, but math competitions usually do not endorse this notation, but it is something you can do, or yeah, but you will probably be writing it as an improper fraction. Sorry, I don't know why I said what is the length of the hypotenuse. That should have been altitude. But yeah. So we have our triangle DEF, and we know that x divides it into lengths of segments dx and xe. Let's say that the altitude from F to DE intersects DE at a point x, and we're given that one of the segments is 4 and one of them is 8. And we want to find this height right here. And we know that D equals 12. Okay. So how are we going to do this? Well, we know that, let's call that this is something EF equals X, DF equals Y. Oh, actually, I would rather not use X because I already used X as the intersection point. So let's just call this A and B. We know that A squared plus B squared is going to be equal to 144. Right? That's 12 squared, right? But let's also have this height h, which we're trying to find. We know that 4 squared, which is 16, plus h squared is equal to b squared. And we also know that h squared plus 8 squared, right, which is 64, is going to equal a squared. That is a very bad 2. So now we're just going to add those two together. So we're going to have 80 plus 2h squared equals 144. And we're going to have 64 plus, 64 is equal to 2h squared. So 32 equals h squared. And if we just take the square root of both sides, we're going to have square root 32 equals h. And if you simplify this, well, you'll see that it's just 4 square root 2. Because it's just 16 times 2, right? And 16 is 4 squared. So that's our answer. Okay, so let's go a little bit more over just the ratio similitude in general. Let's say we have two similar triangles ABC and DEF. If the ratio of the sides of ABC to the corresponding sides of DEF is x, what is the ratio of the area of ABC to the area of DEF? Well, since area is just 1/2 base times height, if ABC has base B and height h, then DEF is going to have base bx and height hx, right? Because they have that ratio. So DEF is going to have area 1/2 times base height times x squared. So the ratio of the heights is going to be x squared. So the ratio of the areas of two similar triangles is the same as the square of the ratio of the sides. So let's say if the ratio of the sides is 3, then the ratio of the areas is going to be 9. So let's say we have two triangles with the same base and different heights. If the ratio of their heights is, let's say, n, what is the ratio of their areas? I'll give you 5 seconds. So they have the same base, right? And of course, these are probably not similar triangles, just to make that clear. These are probably not similar. But if they have the same base and different height, we know that their base is the same, so the area of one is just 1/2 base times h, and the area of the other is just 1/2 base times h times n. So the ratio of their area is simply n. It's not n squared, it's just n, because they still have the same base. Their base doesn't have any ratio, it's just the height that changes. Dropping an altitude is probably one of the most powerful tools you can use to solve geometry problems, especially at the AMCA level. Dropping altitudes to a side can give you a lot of information that you didn't know before. So, for example, in this triangle, we have AD equals DB equals 5, and EC equals 8, and AE equals 4. AED is a right angle. Find BC. So we see no similar triangles, so we can simply create them. We can drop the altitude BH to side AC and just work from there. So we have some kind of thing like this going on. So, oh, that was actually kind of a good one right there. Wait, yeah. So something like this, I don't know, right? It's gonna be. So that's actually a terrible altitude. Let me try to do better than that. Okay, that's better. So we have A, D, E, B, C. And we know that these two are equal to 5, A is equal to 4, and this whole thing is equal to 8. And AD is a right angle. So our goal is to find what BC is. So first of all, what we can notice is that ABH, right? We're calling that H. So triangle ABH, the ratio of the side lengths is going to be equal to, because they're obviously similar, because they share this angle and this right angle, so all three angles are shared. We have AB over AD is equal to 5. So triangle ABH and triangle ADE, they have like their ratio of similitude is going to be 2, right? Because it's equal to 10 over 5. So now we know that AH is just going to be 2 times AE, right? And that's just going to equal 8. So EH is going to be 4, right? Of course. And now we know that EC is equal to 8, so obviously HC is also equal to 4. And for our last thing, we know that from our previous problem, we know that 3 squared plus 4 squared equals 5 squared, so we can just fill in D equals 3, BH is equal to 6, And with the Pythagorean theorem, because BHC is a right angle, we can find out what BC is. So 6 squared plus 4 squared is equal to 36 plus 16, which is equal to 52. And so the area, the answer to this problem is just going to be square root of 52. And of course, we can sort of evaluate this a little further. I think this turns out to be 2 squared 13, and that's our answer. There are also some special triangles that we have to take note of. Let's say we have a right triangle ABC right angled at C. So angle C equals 90, angle B equals 30, and angle A equals 60. The length of the side opposite from the 30-degree angle called, or AC, right, because ABC will be 30 degrees, that will be called X. Then the length of the side opposite from the 60-degree angle must have length square root 3 times X, and the length of the hypotenuse must have length 2X. These triangles are called 30, 60, 90 triangles, and the sides always follow this rule. So when you see a 30, 60, 90 triangle, you can find the other sides if you just have one side. There are also 45, 45, 90 triangles. Let's say we have triangle ABC with the right angle at C. If angle A equals angle B equals 45, then if a length of the leg of the triangle has length x, then the hypotenuse will have length x times square root 2, and so will the other, and the other leg will also have length x, which is a little bit obvious because the two angles are equal. So just to reiterate, this is the 30, 60, 90 ratio and 45, 45, 90 ratio. Thank you all for joining us, and I'll see you next week. Goodbye.